Who did listen to the podcast so far? Absolutely none of you? Somebody? All right. Well, that podcast talks about this guy, Wilbur Atwater, pardon me. And what he did. This guy was pretty incredible. He went systematically through all these various foods and tried to determine the caloric content of them. And from that, he also determined the protein, fat, and carbohydrate content in a lot of foods, and the actual caloric content of the protein, fat, and carbohydrate themselves. So one of the things that was interesting about him is he noted that the peak efficiency of a machine at the time was about 8%. That is the complete caloric or chemical content, chemical energy content of a fuel that goes into a machine. Of that, you only recover about 8% of that energy in terms of mechanical work output. That's actually pretty efficient. However, humans, animals were an order of magnitude larger than that, between 20 and 30% efficiency, which actually is a remarkably good estimate of the efficiency of our metabolism. The values that he came up with are still in use today. They are very good estimates, and they are, in fact, just estimates. But the numbers that he published, what was the date on them here? Oh, 1887. 1887. So, a long time ago, almost 150 years ago, 140 years ago, he said that proteins were about 4 calories, big C calories per gram. Fats were 9, and carbohydrates were also 4. So proteins and carbohydrates are essentially identical in terms of their caloric content. So I'm going to hand back your papers that you did last time, so that when I talk about numbers, you can compare what you did. Okay. Yours? No, I handed you. Theo's. You just get a chance to look and see how well your numbers compared to. You got credit for doing this, for just being here. You didn't. Steph's not here either. She's not here. Anna, you're here. There it is. Wow, you're gone as well. These unusual absentees. I wasn't grading the numbers at all. Everyone who is here got one back? So these numbers here, the first year I did this class, they actually got pretty damn close by an estimate, right? By average. They were remarkably close. I was pretty astounded with that. You guys didn't do quite as well, but you got the general pattern correct. And still not that far off. I mean, hey there, how are you?
How do you know?
I'm surprised you were late. There you go. No problem. Essentially pointing out that proteins and carbohydrates are of equivalent energy value, and that fats are a higher energy density food. And the truth of the matter is that number, that pattern, is thanks to one person in the class. One person threw a super high number up for fats, and I think that if I had taken that data point out, the pattern would have been inverted. A lot of people actually put fats as very low energy dense foods in the class. So yeah, if I had looked at the median or something like that, it would have been a different pattern. But yeah, whatever. It's ensemble, crowdsourced intelligence. So good job, class. And I guess the point, one of the points of this was being able to estimate how much of each of these categories of foods you guys eat, and then, what your relative impressions of the energy content of that is, right? So if I didn't make you take it to the next step, the next logical step, which would have been to have you infer where you're getting most of your calories in your diet from, right? And these are all just estimates. You don't have the actual numbers. It's just you guessing, but it's interesting to know what people's attitudes and thoughts about foods are. So say you're eating very little amounts of fats and large amounts of carbs, but your energy estimates for those two things are off. You may not have a very good sense of where all of your energy is coming from in your diet. We'll look at the other half, the data from the other half of that assignment later. Okay, so this is just a little timeline, kind of summarizing all that history that I talked about last time about the calorie. The big C calorie was first defined back in 1819 by Nicholas Clement. Clement and Carnot. Clement was that guy that had been in the military. And then we had the introduction of these different descriptions of calorie based upon more fundamental SI units, the joule, which is now the contemporary unit for science. And that came in 1888. So if you look at the joule, the definition of the joule, there's all these different definitions of it down there, depending upon the application that the joule can find itself in. The calorie, and this is really the origin of why the calorie is used in nutrition, whereas the joule is used in science more. The calorie really is the sort of more easy to understand in terms of just combustion and the burning of food and like the energy content of food. It's just talking about how much temperature, how much energy it takes to change the temperature of water, a certain amount of water by a degree, right? And that's kind of what our body does. We eat some food, we move around, our body heats up, work happens. Whereas the joule has all these other units. So there's units of force meters, like Newton meters. There's applications for pressure, so a PA is pascals per volume meter cubed. That's for like the internal pressure of something. Kind of hard to think of in terms of the energy content of food, but they are equivalent in terms of thinking about energy. Watt seconds, so how much sustained, how much energy does it take to sustain power, which is a watt, for a given unit of time. So that's really common in like electricity, using electrical measures of energy. All right, let's move on. So we are rooted in the calorie in nutrition, for better or worse. But let's just think about, let's compare these values a little bit. And I want you to like begin to internalize this because this is going to be what the activity is today for you. It's going to require a little bit of this internalization. So set that. 1G of water. It is cubic centimeter. So a centimeter is like the width of your index finger nail, the nail on your index finger, or maybe actually, maybe like your pinky nail. That width of a cube. make a cube that size, so smaller than a sugar cube. All right, a little bit smaller than a sugar cube. That is a gram of water. That's 1 cubic centimeter. That's 1 milliliter. That's 1 gram of pure water. All right, so that's about a gram. So it's the heat required to raise 1 gram, just a little bit of water, about 1/4 degree centigrade. All right, that's hard to estimate, isn't it, in your head? Well, this is something a little more tangible. It's the energy that's required to lift a medium-sized tomato from the ground up to your waist. Just pick it up and hold it, here at waist height. And it's the same amount of energy, because of the way thermodynamics works, that's released when you drop that tomato on the ground. It's the same amount of energy that your body releases every 1/60th of a second. All right, so every second, your body's releasing 60 joules of heat. That's what you're giving off. You're just radiating that. So every 17 milliseconds, your body's just ambiently burning a joule of energy. And that energy is enough to light a 1 watt LED for a second. So a fairly bright LED can be lit for a second with a joule. The calorie, on the other hand, hopefully that gives you a sense of what a joule is. The calorie, on the other hand, a big C calorie, is about the heat required to raise a kilogram of water by 1 degree C. All right, so that's 1,000 milliliters. That's a liter. You can think of a liter as, you know what a liter is like. 2 liters is like a soda pop bottle. Yep. It is the energy required to lift the same height as the tomato, except this time a beach ball-sized boulder of granite. All right, so that would be quite a bit of work to get that up there. Yeah, lifting a beach ball-sized boulder up to hip width or so, hip height, would require a single calorie. It's also the amount that would be released if you dropped that. So you can imagine how much energy a calorie is if you were to drop that boulder from width height onto your foot. It doesn't take that much energy in absolute terms to cause an injury. All right, so this is the amount of energy that you release in just over a minute. So just sitting there, you're burning, not doing anything, not thinking very deeply, not moving around, like knee bounce and stuff, just like zoning out. You've got about a calorie every minute or a little longer. So that's getting at something a little bit deeper here that we're going to talk about, which is basal metabolic rate. This afternoon, if we had been going to Waterville Brewing, that wasn't going to take that long, and I was going to bring us back here, and we were going to do an activity at the gym where you calculate your basal metabolic rate, and we do a bunch of like metabolic tests on our own bodies to determine your own metabolism and stuff like that. It's nothing, no needles, no blood, just like running around and measuring pulse rate and stuff like that. But we're not going to do that. We're instead going to go to Cushnock Brewery in Augusta. Who's been there before? Anyone been down there? Oh, good. This will be fun for everybody then. All right. So, I told you here that what a calorie is. You're burning about a calorie every minute or a little longer. And they typically say that a portion of food, on average, ideally, is about 200 calories. That's not to say a meal, but a meal is composed of portions of different foods, right? And we'll talk about how many calories the recommended intake for a day is in a bit. But,
That would be a good.
Yeah. What? You mean how many calories you consume in a day?
How many calories.
Yeah, well, we can do it. I'll show you the equation. You can do it yourself. We're not going to do that lab. We were going to do it, but we're not going to do it now because we're going to Augusta. So here is a comparison of portions of food that are all about 200 calories. So you can get a sense of the relative energy density of different foods. Here is a can of green beans, peas. They look nice and gray over there on the left. It takes 357 grams of those to equal 200 calories, whereas only 40 grams of M&Ms will get you there. 90 grams of flaxy, seedy bread, whereas only 23 grams of canola oil will get you there. So you can begin to see that in that first one with the green beans, green beans are some protein, mostly fiber, a little bit of starch, right? So you're getting the calories mostly from the starch that's in them, but there's a lot of that food that is insoluble and soluble fiber, right? You're not getting any calories out of it. Whereas the M&Ms, it's pure sugar, right? So you're getting most of the calories there just from sugar. There's not very much fiber. There's not really much fat. There probably is, I guess. In an M&M, there's chocolate in there, isn't there? So there's going to be some protein and fat as well. Canola is just pure fat, right? It's a pure oil. And because of that, we said that fats are about 9 calories per gram, whereas carbs and proteins are about 4 calories per gram. And the bread, even though it's flaxy and does have gluten and some protein in there, it's mostly carb and protein. That's going to be, those are both at the lower 4 calorie per gram, whereas the canola is at the higher 9 calorie per gram, and thus a much more energy dense food. You can begin to compare these things where, potato chips, fairly low number because there's quite a bit of fat in a potato chip, but there's also starch in a potato chip, so the number's higher than canola. Bacon, there is some protein in bacon, pretty much no carbs, but a lot of fat in bacon, and so that number's really down there near the canola, which is kind of the benchmark number. What other ones are interesting in this? Is there any other patterns you guys notice when you're looking at that in the other column? What are the interesting patterns do you notice? Are any of those values surprising to you? Yeah, Theo.
Are like a lot, just like Coke and cheeseburger. It's a lot of them.
Yeah. What does that mean?
Like when you were.
Yeah, and what are you, when you're refining it, what does that actually mean? They're becoming calorically dense, yes, absolutely, but what is actually happening to the food in terms of the constituent components of
I
it?
think for a lot of the sugars are getting.
Mm-hmm. You are so right on it, and you're dancing right around the I'm trying to obviously I'm looking for one thing for you to say to me. What is it? You've got it. Everything you've said is correct. What is it that he's saying but not explicitly saying? When you're refining it, when you're increasing the sugar more than would naturally be there, what does that mean? Sugar more than naturally be there in relation to what? What was I saying about the green beans? Why that number was higher? The grams were higher. How did I describe that food? Yeah. Yeah, there's more fiber, right? So these foods that Theo's describing don't have any fiber in them, right? Where you're eating these carbs in the absence of the other carbohydrates, the soluble and insoluble fibers, the starches even, that they would be naturally occurring with. Okay, so flip to the other side of that. Somebody else. Theo did some hard work there. David, what? Wow, yeah. So, there was a myth for a long time that's still often held maybe by your grandmother or somebody, that celery takes more energy to eat than you actually get from eating it. That is a myth. That is not true. But if you look at this, celery has a huge amount of fiber in it, right? It's you got to eat a lot of the stuff to get 200 calories. It's a calorie diffuse food, not dense. It's a calorie diffuse food. So you feel fuller having eaten 200 calories of celery than you would feel having eaten 200 calories of gummy bears, for example. Yeah.
Does cooking change?
It certainly would, and that is mostly, for bacon at least, that is mostly because as you heat it, you're reaching the melting point of a lot of the more unsaturated fats in there, the more like the ones that have a lower melting point. So then when you eat the bacon, that fat has been removed from it, and you're pretty much just leaving behind the worst fat, which is the more fully saturated fat in the bacon. Yeah, that doesn't really melt out. It really just burns is what happens to it. So yeah, I mean, I wouldn't suggest eating raw bacon anyways, but cooking bacon certainly removes some of the fat content. Yeah, bacon, bacon tastes good, man. And I'm not telling you not to eat bacon, but, in moderation. Okay, yeah, I think we've gotten all the calories out of this slide. All right, so here are you guys. So this is the other half of that assignment that we did last time, that little feedback you gave me. The first two rows are averages across the United States, all right? And the second two rows, I separated out the men and women in the class. They were pretty much the same, but there's a couple interesting, very slight, maybe statistically insignificant trends. First of all, and then the bottom line are the dietary recommendations that are established by the U.S. National Academy of Sciences, which is sort of the nutritionist and biochemist experts that think about metabolism and give recommendations. So a number of interesting things. First of all, the people in this class are very close. Just your estimates of what you eat, and not knowing exactly, but your estimates of what you eat are extremely close to what the recommended norms are by the scientists. So there's virtually no statistically significant difference between what you guys eat and what a healthy diet should look like. That's great. I will show you a slide next week, maybe if I get to it, that looks at the socioeconomic correlates of health, diet, and obesity. And one of the things that emerges is that the higher your level of educational attainment tends to be the sort of healthier your diet is. So, it's good taking classes called biochemistry of food. But then, and I guess digging into the class data, I don't know if it's significant that the women perceive that they eat less fat but more carbs and a little bit more protein, and the men. It was actually, the protein was surprising to me. I would have guessed maybe that men think more about protein. I was wrong about that, I guess. It's just interesting to look at the data. However, the red box here, the problem in America, and we're going to talk about it later, is carbohydrates in the United States, right? So the U.S. eats, and when I say carbs, this again is combining sugars, like simple sugars, the monosaccharides like sucrose and fructose, and the complex saccharides, the starches, the soluble fiber, the insoluble fiber. All right, so it's just combining all into one number, and those numbers are not all soluble fiber and insoluble fiber, right? Those numbers are high because there's a huge amount of simple sugars in the U.S. diet, which is really, in a lot of ways, driving the health epidemic that our country is facing currently. All right. So here is a little bit better table of the USDA estimated caloric needs per day by age, gender, physical activity level, etc. So you guys all fall somewhere within this range for males and females. Are you sedentary? Are you couch potato? If so, men need around 2,500 calories per day. And women slightly less, around 2,000 calories per day. And this is averaged, right? This is not telling you what you should be doing, right? This is averaging across millions of people of all sorts of body sizes and basic basal metabolic rates, but these are just averages. That it's like a starting point. I'll show you better ways of predicting what your caloric needs are in a bit. And then if you're, say you're an athlete that's really active, the other end of the spectrum, so an athlete would need around 3,000 calories per day. What's interesting, if you look at, and a woman would need about as much caloric content as an athlete as the average sedentary male might need. One of the things that you'll notice here that's kind of interesting is there's this, if you look down the entire length of a column, these numbers follow this sinusoidal pattern, right? And really the caloric content needs of an active male peak around their mid-teenage years, like 16, 17, 18 in there, and then they begin to go down. I imagine some of you remember being able to eat, 3/4 of a pizza or whatever when you were 16 years old, and that changes. It changes as you get older. I was a cross-country runner in high school, and I remember that. But and the same is true with women, but the hump on women extends longer, right? So there's let's sort of a shorter, more intense growth period peak for men, and women have a longer developmental period on average. Yeah, so women have this sort of sustained basic basal metabolic need for calorie that persists from their teenage years into their 20s. I don't know if anecdotally any of the people in the class notice that, if women maybe say don't notice a profound change in their appetite from when they were teenagers as compared to what the men may have experienced. But it's interesting. It's interesting to think about. All right. So, any thoughts on that? Anyone? So, basal metabolic rate is this idea. It's like the base amount of energy expenditure that you need to burn to stay alive at rest. So, if I were to take you into that podcast talks that you'll listen to, please do. You'll listen to talks about metabolic chambers. These chambers that's real fun. You get locked in there. They measure the air in there, how you breathe, the food, the caloric intake. They're like basically a human calorimeter, if you want to think of it that way. But if you were to go in there in the dark, chilling out, doing nothing, but laying on a bed for a day, this would be how many calories you would burn. All right, so this is what it takes to keep you alive, day to day to day. If you don't meet it in one day, that's not that big a deal. You have energy reserves, but averaged over a long period of time, this is the amount of calories that you need, basically. And there are these different equations. There's, you can find about 40 different equations out there to calculate basal metabolic rate. They're all, some are more complex. There's ones that are way more complex than this, and there's ones that are even simpler. But essentially, they're looking at things like gender, height, weight, and age, right? So these are some linear equations here that they've been fit to the experimental data that are ways of calculating how many calories you need to burn in a day. And then you can adjust that for your level of activity. Are you sedentary? Do you really just walk from class to the dining hall and back to your dorm at night? Or are you a super intense, rock climber, cage fighter, acrobat, or something like that? I don't know. Marathon runner. Yeah, basal metabolic rate. Pretty straightforward thing. Okay, so this is the last slide I'm going to talk about, and this is all you guys. So here is a basic look at what the world eats. This is data averaged across the whole world. And there's a huge database of this kind of information that that you'll see in a little bit, but this is for the whole world on the right-hand side. And by and large, most of the world eats mostly grains. So a lot of wheat and a lot of rice. There is and I think this data is the most recent that this database goes to is 2011. But there's a lot of sugar. And if you were to go to the database, I can show you, they have data going back to 1961. You can watch these values change with time. That chunk, that wedge, goes way up with time. Some meat, some dairy, produce. And then if you compare countries across the world, like Congo and India, so Congo, this is a place where food insecurity is a real thing. It's a real thing. Food insecurity is a real thing in Waterville. I don't want to say that it's not a real thing. 80% of the kids that go to my children's elementary school are in danger of being food insecure and are on food subsidies. Right? They get school, reduced or free school lunches. So it's here too, but in the Congo, it's a problem that's not being addressed properly, right? That's crazy that you have people with getting essentially half of the calories that they should be consuming in a day. Whereas you look here at the United States and U.S., we have the average, the daily caloric intake average is almost 4,000 calories a day here in the U.S. And I showed you the numbers earlier, right? For an active adult male at the peak, when they are an 18-year-old slam dunking and then running a marathon, running sprints, right? The peak for that, what was the number, 3,200? Yeah, 3,000, 3,200. So the average American eats more than about 600 calories per day, more than the highest potential caloric need of an individual. There are some remarkable individuals out there that are going to be 7 feet tall, beasts that have very high calorie needs, but it's still a pretty remarkable thing.